Something that we are doing a little bit in the afternoon is getting back on the microscope, and a few questions came up on what more can we do with cryo-EM, and part of that comes with what technologies are useful. You heard a little bit more on the processing side. We're going to take a step back and go towards the hardware side. So today we have Anthony Fitzpatrick coming from Columbia University. Anthony, what's the most robust part of the cryo-EM workflow for you?
I'm afraid I'm quite biased. I think that Relion is very robust.
Very reliable.
Yeah.
Okay. Anthony, please take it away.
Okay. Thank you very much, Ed, and thank you all for being here. This is going to go fairly slowly. I only have 20 slides, but I thought that we could talk a little bit about kind of microscopy as a whole, electron microscopy in particular. Have all of you been on a Krios before? Do you feel like you understand how it works? No. So it's very similar to a light microscope. So you have a source of radiation, which in this case is electrons, and you need a series of lenses in order to focus those electrons to be able to form an image. And those lenses were really invented almost a century ago. So the first electron microscope was developed in 1931. The very first one almost didn't really resolve better than a light microscope, so it was barely better than a light microscope. But of course, electrons are intrinsically better for imaging than light because they have a much shorter wavelength. So if you're trying to resolve down to very, very small distances, you're always going to do better with electrons than you are with light. And so the way that electron microscopy developed over the years is there's really two branches. There's material science and there's obviously biology, but there's obviously an awful lot of overlap between the two types of microscopy that we use. In material science, they rely more on amplitude contrast. In biology, we rely more upon phase contrast because we are basically scattering electrons off very weakly scattering objects. So proteins are made of carbon, nitrogen, and oxygen. These are very low molecular, low atomic weight atoms that as scattering centers don't work very well. So we rely upon small phase differences whenever you form an image between the protein itself and the background solvent. And so one of the things that has been sort of great to see about cryo-EM in general is this huge sort of resolution revolution that started to happen around 2013, 2014. Quite a lot of that, as you probably heard in this course, was the detectors. So how we actually detect the electrons coming down the column, passing through the sample, and then going on to the camera. But another part of it also, which is kind of a bit overlooked because we kind of take it as kind of a given, is the quality of the lenses. So the lenses in general, how we focus and basically manipulate the electrons in an electron microscope, really has not changed for almost a century. And it really just relies upon magnetic lenses. So you have a series of lenses as you go down the column that help basically collimate and expand the beam to form an image on the detector. And that has been tremendously powerful. I'm sure you all know, or you've seen, or you will see again tomorrow with Ollie Clark and building models, that in terms of resolution, single particle cryo-EM now is down at the level of almost, it can be as good as 1 angstrom resolution. So you can really get to true atomic resolution. That said, one of the bigger challenges for all of us is going to be to get that same kind of detail and contrast and resolving power in tomography. So I'm not sure how much you've done of tomography yet, but for a lot of us, we do feel, as Ed was mentioning, what's the most robust part of this process. I feel like single particle at this point is pretty good. I think where the field is going to have challenges is in cryo-electron tomography. Some of those challenges are computational, but some of them are just that you need better data to begin with. You will need better images and tomograms of sort of inside cells in order to be able to recreate very high resolution 3D reconstructions of the interior of a cell. So one of the ways that people are trying to sort of achieve this in terms of the hardware side, which is what I was asked to talk about today, is these magnetic lenses are primarily just coils. They are just coils that a current is passed through, metal coils. They then apply a field. That field is localized, and it basically affects the spreading and sort of shrinking and expansion of the electron beam as you form an image. And that has been very, very powerful. In material science, we can get down to 53 picometers, so you can really see a single hydrogen bond using these lenses, but there's always room for improvement. And so one of the alternative ways that we are thinking about trying to improve, certainly cryo-ET, is to use another source of electromagnetic radiation on top. So an electromagnetic field can also be generated as part of is generated as part of a laser. And so we have been trying to, in addition to the magnetic lenses, we're trying to use lasers to actually be able to manipulate the electron beam in order to generate better images for cryo-ET. So the group that kind of led the way on this approach is Holger Muller's lab and Bob Glazier at Berkeley. So in 2008, they started a project where they really were taking a standard transmitted electron microscope. So you have an electron source, the electrons are coming down the column. These are the lenses I talked about. So these circles are just standard electron microscopy lenses. And in the back focal plane, post-specimen, they have inserted what's called a resonator. So the resonator is just a device where you are putting in physically into the column a sort of small sort of metal box which contains two mirrors, and those two mirrors really allow you to bounce back and forth a laser beam at very high frequency inside the cavity. And so what that allows you to do is the electron beam will pass through that laser as it's forming a standing wave in this resonator, and that the electromagnetic field of that laser can be sufficiently high enough to affect the phase behavior of the electron beam. And so the results of this are very dramatic. So this, as you probably all know, is pretty standard for a cryo-EM single particle image. So you can see here that there are very, very weak, low contrast images of the 20S proteasome. So you can see this little trash can type complex just in the images. So there's many of them. And so this is just a standard kind of, if you were to go downstairs and use the Krios, that's what it would look like. If you then use the resonator, where you have this laser bouncing back and forth and interfering with the electron beam, you can now see that the contrast is dramatically enhanced. You can see here that the proteasome is now much, much higher contrast. So you can see much more detail. And so this is being used in a single particle case to show the enhancement. But this could also be very easily applied to cryotomography, and also something that is emerging more in data collection schemes is the 2D template matching that Bronwyn Lucas and Nico Grigoriev have developed, where you don't tilt the stage, but you want to get as high contrast and high resolution images of a given complex. Yes? No, because the sample, in this very simplified schematic of the microscope, the sample is here. It's at this level here. So this is actually where the sample, this is actually an older microscope called the F20, but it's the same on a Krios. So you have the stage is kind of around this level. And so whatever laser you apply, whether it's the resonator or the approach that we use, it's much further down. It can be, you can have it sort of in the back focal plane close to the stage, but we prefer to put ours in principle in the projection chamber, so much further down. And I know that in Holger's work, they have not had problems with like overheating of the sample, right? It's not close enough that it will have a heating effect that will melt the sample. But it's a good question, and a good concern, actually. A lot of people have that concern. I should say, if anyone else has questions, just ask, because we have plenty of time. I only have these 20 slides because they're pretty dense, and so if you have any questions, just ask me. So this was published around 2019, I think, and it's a very nice example of the power of this approach. The challenging aspect of this approach is that electron beam, particularly if you're at 300 kilovolt, is incredibly powerful. It's going at relativistic speeds. It's very hard to deflect that. So you're having to try to deflect a very powerful beam after it has passed through the sample, so in a post-specimen way, and you're asking it to do that with effectively something like this. It's not a particularly, lasers are not particularly strong, and if you want to develop really strong lasers, really powerful lasers, then you get into challenges of safety. How are you going to be able to align the thing? How are you going to be able to not blow a hole in the wall? These sorts of scenario. And so one of the challenges that the Muller group did have was getting up to a sufficiently high laser power that you could actually deflect the electron beam in a clear way to the degree where you can achieve this effect here. So this effect really is achieved by deflecting the post-specimen beam by 90 degrees. The reason for that is that you've probably heard this week about the contrast transfer function. The CTF typically will start at 0, and then it will oscillate like a kind of exponentially decaying sine wave. That means at 0 focus, in any kind of phase contrast microscopy, you have no contrast. You can't really see the image. That's why if we want to find focus, we go to 0 contrast, and then we will slightly under focus in order to generate contrast. So in that standard CTF, you have an exponentially decaying sine wave starting at 0, so you have no contrast at 0. What we would like to have ideally, particularly for tomography, we don't really want to have to blur images whenever we're doing in-cell imaging of neurons, hex cells, whatever it happens to be. We're already struggling for resolution. We want to be able to get as maximum contrast at focus as possible. And so if you were able to deflect the beam by 90 degrees, or change the beam phase by 90 degrees, you can in fact move that CTF from 0 to being an exponentially decaying cosine wave. So now it starts at 1 at 0, and then exponentially decays like that. So this is the principle of this 90-degree number that we all are striving to hit. And this is not the first time that this has really been achieved experimentally. Another way to do this is to use what's called a phase plate, like a physical phase plate. So this was first developed by Nigel Unwin, I think, in the late 80s, maybe 90s, something like that. And what Nigel knew was that he knew that in order to create the phase shift, he would have to have something in the back focal plane that would basically affect the electron beam but not block the beam. And so he knew that it would have to be incredibly fine in terms of a physical plate that goes into the back focal plane to change the behavior of the electron beam. And so what he did was he collected a lot of small spiders. So he put these spiders in a box, let them sort of grow, whatever. And then he let them spin a web. And then that web, which is obviously, the web fiber is about a nanometer thick or less, he was able to coat that with a metal. And that was his very primitive phase plate, and it actually worked very, very well. Fast forward to 2015, I think, Rado Danev, who has spent decades working on phase plates, came out with a phase plate called the Volta phase plate that many of us purchased from Thermo Fisher. And it did work. It does work. You do get this phase shift. The problem with using a physical material is that the physical material, so in Rado's case, what he's doing is he's putting a piece of very thin carbon into the back focal plane, and then he's heating it up. So the back focal plane is where the beam is coming in, and basically it's at its finest point. You're having a focal point there. And he's heating up the carbon. It's releasing a little plume of electrons by heating it. And so that is your very, very small electromagnetic field that allows you to change the phase of the electron beam. The problem with the material is that the material changes over time. So you're trying to heat it, it's emitting electrons, but that's not constant. And so what people would find here and elsewhere is that the phase shift that you would get from the voltaphase plate would change over time. So you would, in, let's say, 45 minutes, you would go from 0 to 90 to back down again, and then you'd have to sometimes move to a different spot on the carbon. So it's just difficult. Also, when you put in a physical piece of carbon, you're also attenuating the beam, so you are starting to lose signal. And so the advantage of this laser approach is that it's in free space. So you really are just interacting a stream of photons with an electron beam. So the electron beam's coming down, you're hitting it with a series of photons from the side, and then you're having an interaction between the two beams, and that is causing a phase shift. Yes?
Yeah, so I guess I don't understand the nanometer. So we try to collect the elastically scattered electrons, right? Not the one that 80% comes.
That's right.
Right?
That's right.
So you try to interfere with those only, right?
Yep, exactly. Yep.
Perpendicular to the.
Yep. You're trying to change the behavior between the elastic and the inelastically scattered electrons. Yes, that's
So
right.
how you avoid the one that 80% transmit through and just focusing on the one that is elastically scattered?
I think that you're able to do that because you're elastically, those ones are at focal point, where the other ones are not necessarily, they're kind of, the inelastically scattered ones have much more aberrant behavior than, the elastic ones are behaving perfectly, right? So they're coming through and they're basically just behaving as they would with the lenses. And you very little scatter with that. When you talk about inelastically scattered, they are going outside of that and are very, very they're kind of everywhere in a way.
Is that one coming straight through them, then how do you separate them out with the one that elastically scattered?
That's what you have your K3 for. So you have at the end of the microscope, when you go into the K3, you have this pinhole, right? The pinhole, you'll see later today, you're really creating a kind of energy filter. So typically, empirically, people have found that 20 EV is the best kind of slit width that you can have. People have tried smaller, people have tried wider. 20 seems to be the best in terms of getting that balance, as you say, between elastically scattered and inelastically scattered. So perfectly elastically scattered would be 0, right? So you're giving it a little bit of spread around the 0, and that gives you your best contrast for them. Does that make sense? Yeah. So in terms of deflecting the electron beam in this way to create a phase shift, what Muller found was that they kind of ramped up to 300 kilovolts. So at 80 kilovolt, they were able to use a certain laser power. But to get to 300 kilovolt, the number that they had to attain was 450 gigawatts, which is an incredibly powerful laser setup. Now what Holger likes to say is that this is now the most powerful laser in the world, which is a little bit misleading because it's not really that it's the most powerful laser in the world. The laser that they're putting in, the laser source, the physical laser that's sitting there on the desk is not the most powerful laser in the world. But if you have a resonator where you have two very sort of, I think it's ceramic mirrors, and you're bouncing back and forth a laser like this, and you're focusing it down to a focal point of maybe 10 or 20 micron, let's say, that's an incredibly powerful sort of photon density. You're trying to hit a very high photon density in order to be able to affect the electron beam. So that number was our target. I had spent time as a postdoc working on a kind of next generation electron microscope where you really don't have an electron source that is continuous. So that beautiful beam that you see downstairs, whenever you're on the Krios and you're doing alignments and you see this beautiful beam that doesn't even have really fringes at the edge, that is a continuous beam. And a continuous beam means that you have a field emission gun at the top of the microscope. You have voltages that are applied that draw off electrons off that FEG tip, and they get pulled down, and they pass through the lens and you form images. The way that the electrons come off is effectively random, stochastic, so that it's like, they're coming off all the time, but they're not periodic. And so one of the people that I worked for wanted to be able to do periodic release of electrons, so like a lighthouse. So you basically have like very periodic single electrons coming off the tip. And so what we would do is we would generate single electron packets that would come down the column. So now you're not doing just random. Now you're timing it so that you have single electrons coming down. The advantage of doing this pulsed electron emission is that you can then interfere that with pulsed photons. So effectively, you can time a sort of laser to be pulsed rather than continuous. So in Holger's case, he is just, this is basically a continuous laser here. So this is a continuous laser. And so same thing applies. There's no timing applied to it. The photons are just coming out at random. But whenever you set up the standing wave in the resonator, that allows you to kind of have some degree of control over the behavior. It's almost like a continuous block of photons that you're passing the electron beam through. In our case, we are trying to synchronize. So we are trying to synchronize the electron packets, the single electron packets, with single photons. And so if we can synchronize it in this way, the big advantage of pulse lasers is that we can use a very, very low average power. So we can use a 20-watt laser. And if power is just energy over time, you can use a microjoule sort of pulse energy, so per photon packet. And then if you package that into a very, very small time window, so remember, your number that you're trying to get to is 10 to the 9, okay? So if you have a microjoule pulse, so 10 to the minus 6, which is the energy, and then you package that into 10 to the minus 15, which is a femtosecond, 10 to the minus 6 divided by 10 to the minus 15 is 10 to the 9. So now you are at that kind of gigawatt type power. And so what we were aiming to try to do was to see if we could phase shift a pulsed electron beam using pulsed photons to basically create the same effect as what Holger had, but to do it in a kind of simpler way. So if you're trying to strobe the beam, so you're not trying to change the gun region itself and try to see if you could, instead of having just a continuous beam, could you actually pulse it instead? There are different ways you could try to do this. So one way that naively you could think about is, why don't we just chop the beam? Or why don't we deflect the beam? So the electrons are coming off. Maybe we could just have a shutter in there that basically just blanks it. People do this with X-rays at beam lines. They have choppers. They have things that basically pass through the beam that allow only a certain amount through. This schematic here shows you that you can do off-axis deflection with a simple kind of little miniature, electric field there. The problem with using some kind of deflection like that is that you cannot control things electronically quicker than about a nanosecond. That's about the quickest you could do. So a nanosecond is 10 to the minus 9 seconds. A picosecond is 10 to the minus 12 seconds. And then a femtosecond is 10 to the minus 15 seconds. So these are all incredibly fast movements. And if you want to trigger a change electronically, you can't really do it quicker than about a nanosecond. Microsecond would be easier. And so this is not really an option for us. The other way that you will increasingly hear about over the next 5 to 10 years is something called an RF cavity. So this is a radio frequency cavity. Not Holger Stark either. Henning Stahlberg at the EPFL now has a Krios microscope, a bespoke Krios from Thermo Fisher, where he has an RF cavity built into the microscope. And so you are there, in that case, you are having a continuous electron source, like a regular sort of fag that you would have on a Krios downstairs. But you are actually using radio waves to chop the electron beam. So you can get very high frequency chopping through using radio waves, because it's another source of radiation. But the timing on this is a little tricky to work with because we're trying to synchronize, in our case, we're trying to synchronize a pulsed set of photons with a pulsed set of electrons. And if the timing is off at all, they're just going to pass each other by and not interact with each other. So the way that we decided to do it was to use laser at the back focal plane. So instead of a resonator, we're just going to put a laser passing through the microscope. So one photon in, one photon out. And then the other way we're going to generate the pulsed electrons is we're simply going to hit the tip of the FAG with a laser beam. And so the photoelectric effect will cause the electrons to come off the tip in a controlled manner. So if you hit, yep. Also a great question. You could have been reviewer one for our paper. So the problem with continuous, I would like to have kept continuous as well, because all the engineering and all the work that has gone into creating the very beautiful beam that you have on a Krios, or formerly a Zeiss or a Joule, it all comes out of this development of wonderful sources of electrons, beautiful FAG sources. The problem if you use a pulsed electron, yes, the pulsed photons do have that instantaneous pulse peak power that you need to deflect the electron beam. The problem is that if you're using a continuous electron beam, that pulsed photon that's coming in is going to hit less than 4% of the electrons, because it's just going to miss them. They're just going to be coming through, the timing is going to be off, okay? And so 4%, you're not going to get any effect, right? So we did that calculation, and that was the number that it came out to be. So for us, if we want to see a meaningful effect, we have to synchronize it, basically. The percentage I think we got is we get about, I think, 80%. The only reason we get 80 and not 100 is because in the results I'll show you today, and I think it was 80, it's around that. In the end, the way that we showed our proof of concept of our approach is the electrons are moving slightly slower than the laser beam. And so the electron packet is not one electron per packet, it's maybe 5 to 10 electrons. And so they're more spread out. And so as the laser comes in and the laser hits the electron packet, some of the ones at the top and the bottom, because they're all Gaussian. The photon packet coming in looks like a Gaussian, and the electron packet coming down looks like a Gaussian. It's why we draw them as Gaussian. So you can see here these little Gaussian packets. And so the ones at the very tail don't get hit because they're just stretched. It's stretched too far. But we hit them enough that we saw a real effect. So in order to basically generate a decent pulsed electron beam, because as you say, the continuous beam should be better, a big kind of change in the field has happened over the last few years. I mean, when I was doing this almost 10 years ago, we would just hit the laser off the tip. It was probably tungsten or lab 6 or something. It was lab 6. And you just get a burst of electrons coming off due to the photoelectron effect. These days, Klaus Roper's, people like that in Europe, JOL, the company, are developing unique photo emission sources. So actually making the FAG more suitable for photo emission because they want to be able to strobe the beam in this way. They want to be able to do pulsed electrons. And so this is 2 papers that they do 1 electron per pulse using 30 femtosecond pulses at a frequency of 10 gigahertz. So to get the kind of continuous beam that you want, rather than having 1 electron, then a lag, a big lag, and another electron, you have to kind of hit it almost like machine gun style. So 10 gigahertz would be like, it would be very, very fast. It would be very, very fast. Like the pulses would be coming in, you'd be getting off a lot of electrons very frequently, And that's how you generate a good electron beam. I think in this paper they got resolution better than 1 nanometer. So you can generate a good beam in this way. There's a second paper where they had something similar from another group that works on this technology as well. And so this is really the basic premise of our experiment, is that you're going to have electron packet coming in. So you see this Gaussian shape that they have. So all the electron packets and the photon packets are kind of Gaussian shaped. So you want to have that coming in. Then somewhere in the microscope, probably the backfocal plane, but you can also put it in the projection chamber, anywhere that it's coming to a point and then going off again. You want to have the pulse photon come in, interact with the electron packet, and then pass through the other side. So in our case, we don't want to have anything physically inside the microscope. We just want to have an optical window. The laser comes in, passes through the very, I mean, one of the things that you never realize about the electron microscope is that the bore is enormous, right, because of the radiation. But the actual path itself, the electron is only passing through a diameter of about 3 millimeters. And so you want to be able to send the laser in, pass through that area, and then leave through the other side. You don't want to have it sort of inside the microscope, or any physical device inside the microscope. And so you have the photon come in, change the phase of the electron packet by 90 degrees. So that's what this overlay is supposed to mean. And then once it comes out the other side, you have this 90-degree phase shift that you have in the electron packet, and the photon goes on its way. Whenever the postdoc and I were starting to think about this experiment, we had to decide how fast is fast enough. And so Daniel Du, who was the postdoc driving this, did a series of simulations, calculations, showing that this sort of schematic here is what you would predict if you were to intersect an electron beam that's pulsed with a pulsed laser beam. And this, effectively what you're looking at is the electromagnetic field if the electron was going into the board. So if the electron beam was going into the board, this is the prediction of the phase shift that you would get. And so you can see in the center that you can get to 90 degrees, that's that yellow, if you had a laser that was faster than about 10 to the minus 11, so 10 picoseconds. So if you are faster than 10 picoseconds, you should be able to get this effect. One other thing that Daniel noticed at that time was that when your electron beam is coming down and you're hitting it with the photon, it's a very, you're hitting it from the side from 90 degrees. And that kick is kind of not circularly symmetric. It's basically a linear kick. And so you don't really want to have the electromagnetic field generated by the laser that's manipulating your phase to be just in one direction. And so the best way of getting kind of more circularly symmetric phase shift is to have two laser beams at right angles. So if you have two of them at right angles hitting the electron beam coming down, it will feel, it really is more like a square, but it will feel more like a circularly symmetric electromagnetic field on the electron beam. Yes?
So when it comes down, right, so it hit the photon, but there's no change in momentum of the electron?
Right, right. It's a completely elastic effect. So you do not have any transfer of energy. No, you could have an energy transfer, but you want it to be completely elastic. You could have an inelastic. So this whole effect is called the ponderomotive effect. So you could have an elastic ponderomotive effect, or you could have an inelastic ponderomotive effect. The reason why you want it to be elastic is you don't want to change the other behavior of the beam. You don't want to change the energy of the beam. You want to simply just change the phase of the beam in this moment.
But if you change direction with, like, say, superconductor magnet, right, you can change direction of electron, but can you induce a phase shift as well, can you?
With a magnet, you can change phase with a magnet. The problem is that the shifts here are so small, right? So the shift to change the phase, you'll see what we did in the end. With only our laser, we were able to generate a phase shift of about 430 radians, and right. So
with that superconductor magnet, we go a lot bigger.
Right.
Okay.
Yep. You'll change a lot more. I mean, yes. So to your point, there is definitely I mean, I started out by talking about these like terrible magnetic lenses that we have. And there's just all sorts of things that you wonder why no one's trying. So you could these days 3D print very different types of electromagnetic lens for microscopes. It's just the view that we have is if it's not broken, don't fix it, right? I mean, it works really, really well. Why would you ever bother to do any of this? But in terms of getting the kind of phase shifts that you need here, and also that balance, as you pointed out, between between elastic and inelastic, right, scattering, you need a kind of scalpel, not a big kind of a lens to do it for you, yeah? So then this is the experiment that we plan to do. So we have the electron pulse coming down, passing through the sample, then you have this sort of laser cross, so you have them at right angles to each other. And in fact, with the resonator approach, this is also now what is being pursued because you do get a more uniform kind of circularly symmetric effect if you do this. And then you get your phase shifted image down below. So the rest of the talk will just be about really how we did this. We only started this project in 2021, and so what we had was a kind of, can you see that? No, you can't see that. So even though I was fully charged, my battery's going to run out. So it's the little one, you know, the tiny one. Right, probably, yes. That is perfect. Thank you so much. Yes. Okay. Thank you very much. Okay, so thank you for that. So we only had, when we started this grant, we only had about 2.5 years, and so we knew that there was very little chance that we were going to be able to do this on a TEM, because getting into a TEM is a lot of work. You have to go through a lot of, it's a much higher vacuum. I mentioned the bore. To get to the actual electron beam itself is very difficult because you have a huge amount of like lead and other stuff on the outside of it. And so we had 2 instruments available at Columbia. One was an SEM, so a little scanning electron microscope. And then the other one was a TEM, which is this is an F20. This is 200 kilovolt. And so we knew that the SEM we could kind of use as a kind of poor man's TEM. So effectively, you have an electron source here, so you have an electron gun. The electrons come down. They go into this chamber, which is quite big. It's quite like you can pull out the shelf. And in fact, this is very similar to, I mean, I'm not sure if you'll see it. I think you will see it this week. The Aquilos instrument downstairs, the FibSem, the CryoFibs, they have this chassis. They basically have the same chassis where you pull out the shelf. And then inside the shelf, you put your sample. And instead of doing transmission, you basically are doing backscattering. So you're imaging the kind of, in a different way from TEM, using secondary electrons and backscattered electrons in order to form an image using these detectors here. So these are your detectors. And so we decided that we would start off with this because it's also lower energy. This was the entire set of optics that we bought to begin the project. So these are all just, for the laser, these are lenses, mirrors, things called periscopes, telescopes. These are just paths that you send the laser through. And then in order to create the room, we had to effectively plan how we would do this experiment. So we'd have the SEM here. It was a very long room, so we decided we have the SEM here. We'll have the laser table in the middle of the room, and then we'll have the TEM on the other side. And so in this way, the plan was that if it worked on the SEM, if the proof of concept worked there, then we could just simply switch the laser optics to the other side of the room, still use the same table, and then just apply them to the TEM side. And so we have this set up. This is what it looks like in practice. So we have the SEM. Then we have our green laser light here, optics table, with all the mirrors and lenses and everything else. And then we have a TEM on the other side. And so this was the setup that we used and developed. So the way that you do this timing that I've mentioned, the synchronization between pulses, is you start out with a laser. You're emitting green laser light You pass that through some mirrors. At some point, you split it into two parts. One stays as green, so that green continues around to the bottom of the microscope where you're going to try to deflect the electron beam. The other half you send through crystal and you frequency double it, so you change it from 512 to 256, so you end up with UV, ultraviolet light, and that ultraviolet light goes to the FEG, because we find that we get more electrons if there's a certain work function for the FEG, and then above that, the energy that you put in, you'll get electrons coming off. So we send the UV to the tip, and so this is what it looks like. So you have obviously a lot of green everywhere. This is with the lights off. The SEM itself is here, and those periscopes, telescopes, the SEM we had has a very small optical window, so you can see this kind of optical window through it, and you can see like a little piece of tungsten in there. That is your FEG tip. It's a Schottky tip, but it is zirconium oxide coated tungsten. And you can actually see in there, I don't know if you can see it on the screen, but you can certainly see this bright light. It's like a little light bulb. So when you're hitting it with the UV, you're getting a lot of electrons coming off. And the way that we control the synchronization between the green laser light and the sort of UV generated electron beam is, you could imagine that they could have different timings, right? So one comes in, the other one misses it by a mile. And so we have this, it's called an optical delay line, and all it really is, shown here in black, this is just a mirror that moves along a track. And so you can position this mirror wherever you want. And so whenever you have perfect synchronization between the electron packets and the green laser beam coming in, that's time zero. That's called time zero. So that's where you find perfect synchronization. A lot of this setup, at least for this proof of concept work, we had to do some kind of, every morning Daniel would come in and he'd have to try to find the beam again and get the electron beam as high as it could be. And so the way that he did that was, in directing the UV to the tip, you have these periscopes and telescopes, that are there, but you can actually control those with motors. So you have XYZ motors, and the easiest way to control those motors in order to guide the UV to hit the tip itself is to use an Xbox controller. So he would basically use the Xbox controller to basically guide the periscope telescope into the right position to get the electrons from the tip. So you've got 15 minutes. So with this then, you are now trying to show in a very primitive, simple way that if I have electrons coming off the pole piece generated by the UV, that they pass through some sort of interaction volume where I am sending in green photons and then out the other side, that this can somehow act as a simple lens. So this electromagnetic field of the green laser can effectively act as a lens on the electron beam. And if you were to defocus this electron beam, you are going to, by definition, change the phase of that electron beam. And so this is the very simple proof of concept that we wanted to do. In order to show this, we had to have some kind of a thing to image, some sort of spatial filter, so something with fine detail. And so we used the Chris Russo Hexi foil grids that are, they have holes of about 290 nanometer, you can see here. And then from when the electron beam hits that, those secondary electrons come off, and then they get detected by this detector, and then you form your image that way. So this is what it looks like. The great thing about that chassis is that the shelf, when you open it up, I can put my head inside the entire chamber. It's that big. And so in so doing, you can actually put a lot of optics inside the chamber. So you have, so actually our green laser is coming in from this direction here. It's then going up through a periscope. So you have a mirror here, and then you have a final lens. And then you're focusing that laser beam right down to a very fine point directly under the pole piece. So this pole piece is where the electrons are coming off. And then you're passing the photons out through the other side, and then they go down a periscope and onto some photon dump outside the microscope. So you really are going in, hitting the beam, the electron beam, and then coming out again. And so the big result of the experiment was the following. So These are the holes in the hexafoil grids. They obviously look somewhat holy, but we are on the 4th floor in a very bouncy building, and so the resolution is not what we would ideally like, but we can see the holes. And this is at time 0. So this is where the electron beam and the laser beam are interacting. The pulses are interacting synchronously, okay? Then you have some reference point way off from time 0. So I think we used 21 picoseconds away. So now the electron beam is coming in, and then 21 picoseconds later, the laser beam is coming in. So they're not interacting at all. And so if we take, a lot of these types of experiments are predicated upon difference images. So if we take the difference between these two images, if there is no effect, the image should be completely flat. If there is an effect, we should see a difference. And so if we subtract the reference image from the time 0 image, we see that there's some sort of a darker spot in the middle, and then there's a brighter lobe on the outside. And in grayscale, it's not super clear, but if we do that now on a color scale, you can see here that this is the experimental image. So this is the experimental different image. So you can see here a minimum in the center, and then sort of a maximum on the outside. So you have 2 lobes on the outside, and this is the direction of the laser beam here. So across that direction, you are seeing some sort of change in behavior of that electron beam, okay? And we tried to recreate that using simulation to show that this is what you would expect to have from the timing and the laser power that we were using. And you can sort of see that the simulated difference image is similar, certainly in terms of the magnitude of the effect. And so that difference that you see in terms of the electrons being weaker here and stronger here, if you then integrate this image, you can actually plot this difference, and you can see that in the experimental line, shown here in yellow, those electrons, which should have just passed through the hole, are now being pushed to the right-hand side and to the left-hand side by almost a micron. So they are being pushed by 500 nanometer and 500 nanometer on either side. And that shows you that you are actually doing this defocusing that we had claimed we wanted to try to do with the electron beam using a pulse laser beam. So that is a proof that the effect has worked. But what does that proof actually mean in terms of phase shift? So if you have a, this pulse coming in, the green pulse coming in, this is now where we convert that sort of movement of the electron beam, that kick. So obviously if they're being spread like that, there's some sort of a momentum kick that's happening to the electron beam. And so we can quantify that. So the momentum kick looks like, as the laser comes in, you end up getting one half is kind of increased, the other half is decreased. You end up with a momentum change of about 45 microradian on each side. And that momentum kick can be converted into a phase shift. And that phase shift, as you can see here in the other plot, so this sort of ellipsoid in the middle, that's just the electron beam coming down. That's the electron beam coming into the figure, and the laser is coming across. And so now your phase shift that you're seeing in the region of the center of the beam goes up as high as 400 radians, 430 radians. I mentioned 90 degrees. 90 degrees is pi over 2. You are 2 orders of magnitude higher in terms of the phase shift that you need. So we, in worrying that we would not hit this effect, we massively overshot the effect. We got a much bigger effect than we needed. Talking about the voltage phase plate earlier and about how it changes over time, we wanted to show that the phase shift that we get of this 430 radians is constant over time. And so to do that, this is just a plot of the difference in intensity in that image where we have the time 0 and the difference and the reference, and we're doing the difference image. So in that difference image, as I said, if you have no effect, you should go to 0. You should basically have a flat image. So that's what happens in the control. But in the experimental case where we are synchronizing the 2 pulses, we get a perfectly kind of pretty flat line going across over 10 hours. So over 10 hours, we get that phase shift of 430 radians, plus or minus, well, it deviates by about 1.3%. So it's pretty stable. And then, of course, this is just a proof that effectively if you were to change the pulse duration. So if you were to use a slower pulse, because that's always easier than using faster pulses, the effect goes away. So you can start to see here that if you use 6 picosecond, 8 picosecond, 14 picosecond, the Gaussian is getting shallower each time. So that's obviously making the effect weaker. And then spatially, if you were to have misalignment between the laser beam and the electron beam, so if they're not overlapping perfectly, it also goes to 0 as well. So this effect, we kind of parameterized around it and what makes it. One of the reasons why we like this approach and why we'll continue to pursue it is because one of the things about tomography in particular is that the pulsed sort of approach is more flexible in a way, because whenever you do a tilt series for tomography, and increasingly more and more of you will be doing tomography, the focal point of that tomogram actually changes, so it actually moves. And so if you have a resonator in place where you are putting a continuous laser, bouncing it back and forth, the resonator is fixed. You cannot move that resonator. However, if you're putting in a laser beam from outside the microscope, focusing it down and then expanding it again and letting it dump out elsewhere, you can actually move the focal point of that beam up or down, to the left, to the right. That's all controlled outside of the microscope. So you have a lot more control of the interaction between the electron beam and the laser beam. When you synchronize the electron packets and the laser packets, you also have much less chance of aberrations happening, because obviously when you have a standing wave and you have electrons passing through that, you're never quite correctly timed. So you're hoping that the electrons hit the laser, but they won't necessarily interact perfectly. And so whenever they're perfectly synchronized, you have less of a chance of getting aberrations. And I think that one of the big things, I guess, that's pretty obvious about this approach is that if everything is outside the microscope in terms of the laser, you can control everything from outside the microscope rather than having to work with something inside. The vacuum inside a TEM is very challenging. The access to the electron beam is very challenging. All those things are very challenging. So you would ideally like to have everything else ex situ. And then the final thing, and we're going to end on this pretty much, is that all those other lensing effects that you can have in a microscope are pretty well controlled by magnetic lenses. But things like aberration correction and so on, there is increasing evidence that you could use lasers for like little tweaks like that, because they're a scalpel. They are a way of doing this in a very fine way. So the next steps for us are to take this room further. We've done the SEM study, the proof of concept. Now we're going to try to do it on the TEM side and ramp this up to at least 200 kilovolt. We don't have a Krios to spare, unlike Ed, who just told me he has a Krios to spare. But we have a 200 kilovolt, and we'll try to do what we can with that. I mean, it's not the best microscope for tomography, but it does have a K2 detector on it, so we might be able to do things like template matching as well. And in that case, we will send the UV pulse into the tip here, and then we have two options. We can either send the green light in at what's called the octagon, which is around the stage, around where the sample actually sits, or we can try to put the green pulse down in the projection chamber, because it also crosses over there. You have a crossover there as well. And try to do it that way. But one way or another, we're going to try to see if this could work in a TEM. And so the paper, if you're interested, we just published it in eLife on this proof of concept work in the SEM. One of the people that we work very closely with now on photo emission is a group at Cornell, Jared Maxon's group, because Jared actually develops new materials for photo emission guns. So you don't want to be just doing tungsten or Lab 6. You want to have dedicated kind of new alloys that allow you to get the maximum, most coherent electron beam coming off a tip if you shine it with a UV laser or green laser. Daniel led the whole study very, very well. He's now moved on and is working at the FDA. And then some of the technicians that work at Zuckerman, who built a lot of the optical ports for us. And thank you for your attention. That's it. Yeah.
So how the system, same that's similar to the one that at Berkeley, where they use that display to not they use that, right? They tried it. How's it different?
How's it different?
Yeah.
So in their case, I mean, it really was, as you pointed out earlier, it's really a difference between continuous and pulsed. So in Holger's case, it's completely continuous. So they would be using the same electron beam that you would have on the Krios downstairs. There's no need to change the emission or anything. They put in a physical box into the microscope. So you have to have a cavity. And in fact, I believe, I'm not sure, Ed would probably know better than me, I think on the Krios 5, you can now actually buy a Krios 5 with that extra space if you want to insert a resonator, let's say. Because this is probably going to happen for the field. One of the ways that tomography will get better is just to get better primary data. So they put in a resonator. One of the challenges with the resonator is that once it's in, it is fixed. You cannot change it. It is going to sit there. The mirrors are going to be there. And I think that some of the challenges with that are the following. Number one, you have to pass the electron beam into the path of the focused laser beam. So you can't move it, right? So you're going to have to bring the laser beam, the electron beam down. And then I think from the latest presentation I saw, they have to move the electron beam into the path of that laser. Now, when you do that, you are going to lose resolution because you are now asking the electron beam to do something it doesn't really want to do, right? The other challenge I know is that the photon density is so high that those mirrors can actually start to deform and melt. Not melt fully, but they have to be very, very precisely machined in order to get the correct focusing of the laser beam. And under such high power, so gigawatt power, you can end up deforming those mirrors. So those are experimental challenges, but it works. You can see from the first images I showed, it works really, really well. You know, they have some aberrations there. Like they also have things called this kind of white stuff as well. They have things called ghost images that happen, which I kind of alluded to in the timing aspect. So when you time things, we predict that you would have less aberrations when it's perfectly synchronized.
External and tunable and external.
Right. That's right. That's right. And no resonator. So you really are just doing, you have an optical window. You literally have a window where we can, when I say a window, I mean we can go up to the microscope and we have just put in, we've drilled a hole and we have put in a vacuum sealed, O-ring sealed port where you have some metal, and then in the middle you have laser transmittable, you know, glass, can tolerate high fluence lasers, and you can literally see into where you're going, and then I goes like. Right. So our SEM was only 30 kilovolt. So we have to go up by, in principle, you know, an order of magnitude to 300. But our test microscope would be 200 kilovolt, which is kind of, once you're at 200, it's pretty much the same. Yeah. Yeah. Any other questions? You sure? Now is not the time to be shy. So, no? Okay, well, thank you, Ed. Thank you, everyone, for listening. Thank you so much.